many thanks, Erica, for the kind introduction, and of course also for giving me the opportunity to speak here in the Climate Coffee series. I highly appreciate that. And I'd like to present some work that I've been doing together with Lukas Papritz at ETH in Zurich. And you can read from this title slide here that we entitled that bit of research, Quantifying the Physical Processes Leading to Atmospheric Temperature Extremes. And so why studying temperature extremes? I mean, that's, I think to most of us, it's kind of a no-brainer. Most people agree that these events are super important just due to their impacts. And I'd just like to underline this here in the beginning very briefly with a few statements from famous previous studies. So for instance, Robin et al. Here in 2008 find about 70,000 people passed away during the 2003 heat wave due to that event. And of course, you could argue here about the exact numbers and how they come about, but I think by and large, it's agreed that these events have large numbers of fatalities attributed to them. Coates et al. Put heat waves in perspective with other natural hazards and find more fatalities in Australia due to heat waves than from all other natural hazards combined. These events are changing. Vicente Cabrera et al. Find 37% of heat-related mortality attributable to climate change, looking at many different locations in different countries. It's not just health impacts, it's also ecosystem impacts. A famous study from 2005 here finds Europe-wide reduction in primary productivity caused by heat and drought in 2003. And it's not just the hot tail that causes impact, but also the cold tail. And here colleagues from Korea find a sharp increase in traffic accidents in Seoul below a certain temperature threshold. So I think that just these examples, and you could come up with many more of that kind, show that it's very important that we as an atmospheric dynamics or atmospheric science community provide a quantitative physical understanding of these events. And I think this really quantitative process understanding is absolutely crucial in particular in two aspects. So the first is when we think about physically plausible storylines of high impact temperature extremes. So for instance, if you think about unseen events in a certain location, but also if you think about future temperature extremes in a warmer climate. And the second thing where we need this process understanding is when we want to evaluate climate models regarding how realistically they simulate the physical functioning of these events. And of course, that latter point is super important if you think about the robustness of projections of heat extremes in a warming climate. Now, obviously, we're not the first people to think about how temperature extremes function. There's a vast body of literature on that already. And if you look at that body of literature in detail, you find that essentially three processes pop up over and over again as being important for the generation of temperature anomalies during hot and cold extremes. And these three things are, firstly, the advection of air across climatological temperature gradients. So the idea that you can move air from a place that's climatologically warm to a place that's less warm, and that will, by and large, generate a positive temperature anomaly. And conversely, if you move air from a cold place to a warm place, that will give you a cold anomaly. And the second thing that often is mentioned, in particular in the context of heat waves, is adiabatic warming and subsiding air masses. So if you have an anticyclone, you have large-scale subsidence, and then that subsidence air gets compressed, and through that it gets heated adiabatically. And that's been noted in many instances as being important for heat waves. And then the third point that I list here, diabatic processes, is really rather a basket of different processes. So what I mean with diabatic processes is any process that changes the potential temperature in an air parcel. Yeah, so that could be, for instance, cloud diabatic heating, that could be free tropospheric radiative cooling, but in particular in the context of heat waves, what's important is sensible and turbulent heating of air near the surface. So the sun heats the surface, and then the surface heats kind of the lowermost air through sensible and turbulent heating. And so with that, it's clear that I also list all the important work on land-atmosphere interactions during heat extremes, soil moisture, and the like under this point. Right, and so kind of what I want to convey with this slide is essentially we know what the basic processes are that generate temperature anomalies during hot and cold extremes. However, there's not much of a consensus about the relative importance of these processes for temperature extremes, and that's the research gap that I'm addressing in this talk. I'll do this in this following way. So I'll firstly introduce a method that Lucas and I developed, which is a Lagrangian temperature anomaly decomposition, which allows quantifying the contributions of these exact three processes to any temperature anomaly of interest. And then what we'll do is we'll apply this approach to near surface temperature anomalies during hot extremes from all across the globe. And then sort of the last 2-3 minutes, I will extend that analysis to cold extremes from all across the globe. So all the analysis that you see here are based on Leader 5 data, and they're published in 2 papers by Lucas and myself. So one in Nature Geoscience and the other one in GRL. Okay, so this Lagrangian temperature anomaly decomposition is really kind of the backbone of what I'm presenting. So I'll take a few minutes to introduce you to that approach. And so here's how that method goes. So we start from the thermodynamic energy equation, which is the equation 1 here, and that tells you how temperature T changes in an air parcel along a trajectory. Yeah? And so you have 2 terms on the right-hand side. So the first term has this omega in it. So omega is vertical motion, and so that's the adiabatic compression or expansion term. And then the second term has this material change in theta in it. So that's the diabatic heating or cooling term. Yeah. And when we speak about temperature extremes, we're sometimes not only interested in the absolute temperature that a certain event reaches, but rather also in the temperature anomaly relative to some sort of temperature climatology, because at the end of the day, a temperature extreme is nothing else than an unusually large temperature anomaly. Right, so what we do here is we plug in T equals T bar plus T prime in this equation 1. And T bar is some sort of temperature climatology, and T prime is the temperature anomaly relative to that temperature climatology T bar. If you do that and just juggle around terms a little bit, you arrive at this equation 2 here, which is the Lagrangian temperature anomaly equation. So that equation tells you how a temperature anomaly T prime changes in an air parcel along its trajectory. Yeah? And so there's 4 terms on the right-hand side. So the first term is usually small, and we'll consider it as a residual for anything that I present here today. And then the second term quantifies how much temperature anomaly you get if you move an air parcel horizontally across climatological temperature gradients. So that's this advection term. Yeah? And then the third term, again, has this omega in it. So that's the term that tells you how much temperature anomaly you get from vertical motion. So that's basically the adiabatic effects on temperature anomalies. Yeah. And then the last term is again the diabatic heating term. Now, equation 2 allows to decompose any temperature anomaly of interest in the following way. So what you do is you start from a place X and time T. So maybe you select a temperature anomaly that you like, maybe a heat wave. And then what you do is you compute a backward trajectory from that location X and time T. So you follow that air parcel back in time until the time when the temperature anomaly in that air parcel was last 0. That's what we call the genesis time, or the genesis location of the final temperature anomaly at location X and time T. And then from this genesis time and location, you simply integrate your equation 2 here along that trajectory, again in the forward time direction until you're back where you started your backward trajectory, until you're back at location X and time T. And because equation 2 exactly describes how temperature anomaly changes in an air parcel along its trajectory, this yields a decomposition of that final temperature anomaly into 4 terms. And again, the first one's usually small. We call it the seasonality T prime. And then you have an advective, an adiabatic, and a diabatic contribution to any temperature anomaly of interest. Okay, so here's how that goes for a real-world trajectory, just to illustrate this a bit better. So you can see here in the top right an example trajectory that I computed backwards from this location here, which happens to be Lytton. So this is kind of a place that got struck very heavily during this infamous Pacific Northwest heat wave that hit that region in June 2021. And you can see here this air parcel trajectory, and so this air parcel sort of crossed the North Pacific, did this little loop here, and then curved anticyclonically towards the location of Lytton. And now in the top left, you can see the temperature in black, solid, and the temperature climatology, always at the location and time where that air parcel is located. Yeah? And now you can see, if we go back along that trajectory for about 4.5 days, that's the time when the temperature anomaly was last 0 in that air parcel. And the location where that happened is indicated here with the red star. Right? So the final temperature anomaly formed over this portion here of the trajectory. What we do is we integrate our equation 2 along this portion of the trajectory here, and that then yields these colored lines, which are shown here in the bottom left. So you can see in black the temperature anomaly in the air-parcel as a function of trajectory time. And then you can see the advective, adiabatic and diabatic contributions in the different colors here. And if you do this integration business all the way to the final time, till air-parcel is located here again, this yields the decomposition of your final temperature anomaly at this location. And in this particular case, you had a temperature anomaly of about 19 Kelvin, so a huge temperature anomaly. About 13 Kelvin of that was from the adiabatic term, about 4 or so from the advective, and then small contributions from the other two terms. So this is really just an example. It's not representative for how this heat wave functioned, but just to illustrate how this method goes. Now, there's two further characteristics of temperature anomalies that you can infer from this approach. One is kind of the temporal scale over which these anomalies form. That's what we call the Lagrangian age of a temperature anomaly, and it's simply the time difference between the genesis time here and the time of interest. So that would be 4.5 days in this example. And the second is kind of the spatial scale over which these anomalies form, and we compute this here with a measure that we call Lagrangian information distance, which is simply just the great circle distance between the genesis location and your event of interest. Okay, so on to some real results. So when Lucas and I started this work, we realized there was really no consensus at all about how important these different processes were for temperature extremes across the globe. And we looked at individual studies, and we realized that previously individual studies, they always either focused just on individual events, kind of case studies, and it's difficult to generalize, or they looked at individual processes, but not all of them together, or they just looked at individual regions and heat waves in selected regions. And so what was really lacking was kind of a global quantification, these three process contributions to temperature extremes, and we felt that we could contribute to this discussion with our approach. So what we did is we identified hot extremes all across the globe. We took so-called TX one-day events. So that's a very simple definition of extremes. So you just take the 2-meter temperature time series at each ERA 5 grid point, and then you ask what is the hottest day of the year in each year. So we had 42 years, and so at each grid point we had 42 hottest days, and these were our temperature extremes. We call them TX one-day events. Yeah? So it's not the largest anomaly, it's just the largest absolute 2-meter temperature in the daily mean in each year at each grid point. Yeah? So 42 events per year. Sorry, 42 events per grid point, 1 per year. And then we computed backward trajectories from all of these TX one-day events from all across the globe. And we considered near surface levels. So what I speak about is near surface temperature anomaly. So we considered the levels 10, 30, and 50 hectopascals above ground, so kind of the lowermost 500 meters of the atmosphere. And we computed backward trajectories every 3 hours during these events. So that's 8 trajectories per level and TX one-day event. And so since we have 3 levels, it's 24 trajectories per TX one-day event. Right, and since we have 42 of these TX one-day events at each grid point, we had about 1,000 trajectories that we could analyze at each grid point. For each of these trajectories, I computed the Lagrangian temperature anomaly budget, and that allowed us to construct these global maps here that you see. And that's kind of the key result that I want to convey in this talk. So you see in the top left, TX one-day T prime. So that's the average near-surface temperature anomaly during the hottest day of the year. Yeah? And panels B, C, and D show the advective, adiabatic, and diabatic contributions. Yeah. And now you can see here the largest temperature anomalies during TX one-day events we have over land here, Canada here, Siberia, Australia, smaller anomalies here over the ocean, still considerable anomalies over storm track regions. And now what I want to do is really just walk you through some basic structures in these maps. And we start with these storm track regions. So in these regions, you see large positive advective T prime, nearly 0 adiabatic T prime, and negative diabatic T prime. So what happens in these regions is after anomaly genesis, air parcels contributing to TX one-day events in these regions, they travel poleward, thereby they acquire their advective T prime. They do that more or less in near surface levels, hence little adiabatic T prime. And because they're moving towards increasingly cold ocean surfaces, they get cooled through sensible heat fluxes from the oceans underneath. That's why you have this negative diabatic T prime. But the key thing to note here is the only positive contributor to positive temperature anomalies during heat extremes in these regions is the advective term. So advection is what generates the positive temperature anomalies during heat extremes in the storm track regions. It's a whole different story if you go to these tropical, subtropical land regions. There, the advective T prime is negative. Adiabatic T prime is still kind of smallish, most regions at least. Now the big thing is these diabatic T prime here. So there, what happens there is air parcels approach the respective TX1 location from climatologically colder regions. That's why they have this negative advective T prime. They still do that more or less in near surface levels, and they get strongly heated diabatically from the surface underneath. And now here in these regions, the key thing that builds up positive temperature anomalies during heat extremes is the diabatic heating. Now, there's other regions, for instance, in the Mediterranean, but also near major orography, where the adiabatic term dominates. And then there is many regions where you need a combination of different processes. So for instance, Scandinavia, also Western Russia, we have positive contributions from all three processes that build up these temperature anomalies during heat extremes. Near surface temperature anomalies, I should emphasize. Okay, so onto the maps of the Lagrangian age and Lagrangian formation distance. On the left, the temporal scale over which these anomalies form, and on the right, the spatial scale. And what I want to highlight here is really just spatial variability. So you can see there's some regions in the globe, for instance here, tropical West Africa, where these temperature anomalies that lead to heat extremes form kind of within 1.5 days and within just a few hundred kilometers, kind of a local thing. And so there in these regions, you wouldn't do too much wrong if you just analyze these events from a solely Eulerian point of view, if you just looked at the local weather maps. Yeah. It's a whole different story, though, if you go to Greenland, for instance. There, the Lagrangian age of these temperature anomalies is on the order of 5 to 6 days, and the scale over which these anomalies form is on the order of 2,500 kilometers and more. So there, the formation of temperature anomalies leading to heat extremes is an inherently Lagrangian business. And it's a bit similar to precipitation extremes. So we're all aware of the fact that the precipitation or the water that rains out during a heavy precipitation event didn't evaporate locally or instantaneously, but rather accumulated in the air, sometimes over long distances and long time scales. And it's a bit similar with temperature anomalies leading to temperature extremes in certain regions of the globe. They too accumulate over long distances and long time scales. Okay. So the key findings of that part, so all terms dominate in certain regions of the globe, so advection in storm tracks, adiabatic warming near major mountain ranges and parts of the subtropics, and a diabatic heating over tropical, subtropical land areas. But very often you also need a combination of these processes to generate heat extremes. And then we've seen that the temporal spatial scales over which these anomalies form are on the order of hundreds to thousands of kilometers and maybe a few days. Okay, so on to cold extremes for the last 2 or 3 minutes. So cold extremes are kind of fun to think about in some sense, because you can learn quite a bit about how they must form just from looking at this equation here, which is the Lagrangian temperature anomaly decomposition, when recalling that cold extremes are nothing else than unusually large negative temperature anomalies near the surface. So this equation tells us that we have 4 options to generate them, but as for hot extremes, the seasonality term is usually small, so it leaves 3 options, which is the advective, the adiabatic, and the diabatic term. And it just turns out that this adiabatic term doesn't help much for generating large negative temperature anomalies near the surface. And that's because in order to get to the surface, air either must come along the surface, in that case, omega is small, and then you get pretty much 0 here, or air must subside to get to the surface, and in that case, omega is positive. And it just turns out that this bracket here, which tells you how much temperature normally you get per unit subsidence, happens to be positive pretty much everywhere across the globe, and has to do with the fact that climatological stratification is stable across the globe. And so basically that tells us that this term here can only be positive for near surface temperature anomalies. So it doesn't help to generate negative temperature anomalies. So that leaves only advection and the diabatic term. Now, if you think about the coldest places on Earth, the climatologically coldest places on Earth, by definition of climatologically coldest, you can only come from a warmer region, right? And in that case, the advective term has to be positive. So that doesn't help either in the climatologically coldest regions. So this already tells us that in the climatologically coldest regions on Earth, the only way to generate the cold extreme is through diabatic cooling. Elsewhere, the question is whether this diabatic or the advective term dominates. Yeah? Now, here's the result of this analogous analysis for cold extremes, which is published in the GRL paper. Same setup as before. Top left is Tn 1 day T prime, so the temperature normally on the coldest day of the year. And you can see this adiabatic term here is positive, as we have seen already when looking at the equation. And if you go to the climatologically coldest regions on Earth, here in the Canadian archipelago and in Siberia, there indeed you see a dominance of the diabatic term, and the advective term is small or positive. And if you go to other land regions, for instance, Europe, it's kind of a combination, advective and diabatic. And then over oceans, it's kind of the advective term that dominates, because the ocean is the big enemy of large cold anomalies, because the ocean likes to heat up anomalously cold air. Right. Okay, but at the global scale, kind of the advection panel here is the dominant one. All right, so I come to the summary already. So at the global scale, advective T prime is the dominant contributor to near-surface temperature anomalies during cold extremes, and there's kind of a transition from advectively dominated cold extremes over oceans to more and more diabatically dominated cold extremes over the coldest regions on Earth. In some regions, it's a combination of the two, and I just skipped over this for time. But in most regions, the cold so the Tn 1 day anomalies are older and form over larger spatial scales than the Tx 1 day counterparts. So cold anomalies form over longer time scales and longer spatial scales than hot extreme temperature anomalies. All right, so with this, I'm already at the end, and I thank you for your attention.